soft and gooey. Bitumen is soft, and high rank anthracite coal is extremely brittle. So the material itself changes with maturity. Also, there's some evidence that Vernick published that during the course of maturity, some shales develop little microfractures, which would contribute to its brittleness also. Okay, let me just head on. Well, here's just, I'm sorry, a plot that actually had nothing to do with gas shales, but I wanted to show you something. On this plot, horizontal axis is acoustic impedance, vertical axis is V/PBS ratio. And this was a field somewhere of interest. And the point is, in rock physics, we often are able to locate different lithologies. For example, this ellipse would be about what we would expect. Wet sands, oil sands here, gas sands here. Shales would be up here where the reds are. Carbonates are often over here. These are actually some coals. So if we have enough geophysical measurements and we have local data to calibrate to, there is some reason to think that, well, perhaps we can see indications of more calcite in our rock or more quartz in our rock. But again, this would have to be very site dependent and calibrated. Keep pushing on me, Arthur. Don't let me run away. I want to just run to the end here because you've seen some of this. Certainly, shales are anisotropic. This is a pretty typical lab measurement. We have the velocity. Horizontal P-wave velocities are about 20% faster than vertical, and same with shear. That's not surprising. Lev Vernick, back in the 1990s, published data that he measured at Stanford, where he found that the organic-rich rocks tended to be very anisotropic, or often were. And so the vertical axis, it's not really a Thompson parameter. It just says, for example, 1.1 means the horizontal is 10% faster than the vertical. It's just a ratio. And he found that the low Carrigan rocks, have pretty typical shale anisotropies, 5%, 10%. But these rocks with 13, 20, 30% by volume organic carbon had unusually high anisotropies. It's not monotonic, so we have to be careful there, but certainly that is a possible indicator. Tiziano Benorio allows me to show a few of these slides. Now, organic-rich shales, again, are these mud-sized, tens of micron-sized particles. They can have inorganics like clay, silt, calcite, carbonate, quartz, and then the organic materials, which are macerals, oils, gases. And these are, on the left is a scanning electron microscope, and on the right is what's called a confocal laser scanning microscope image. In other words, organic materials fluoresce. So under the proper illumination, the organics glow nicely, and the minerals just stay black in the background. So we're actually looking at little nano-sized particles here of organic material in the shale. The famous Van Crevelen diagram kind of indicates why it's so complicated. Now, these are not geophysical axes, but they're relevant. The vertical axis is called the hydrogen index. It's a measure of how much hydrogen. Actually, after all, we're talking about hydrocarbons, so the hydro part is the hydrogen. And the horizontal axis is a measure of the oxygen. Now, these dotted curves are contours of maturity. So way out here, this would be a very immature peat or very young organic material. And as it moves down to here, it starts maturing a little bit, and here more. So going from upper right to lower left means it's maturing, giving out gas, oil, and so on. And now, different initial compositions have different histories. So there are some materials that could be deposited up here, and they will be oil prone. So they would move along a path like this, and as they mature, they're more likely to give off oil. A material that was deposited over here, as it starts maturing, would tend to give off gas. And then down here, this wouldn't give out very much at all, but if anything, it would be gas. And down here, this is basically inert. And the end member down here is graphite. No, graphite is TOC, but it's not useful unless you're a pencil manufacturer. Right? So we have to be, this is one of the complications. TOC itself is not a universally useful number. It has to be in the context of your field where you know the maturity and other things like that. These are some data that were measured by Vernick and I think replotted by Tiziano and Orio. Basically, here's the P wave velocity, and this is effective stress. Now, in general, we expect velocities to increase as we increase the effective stress. It's a very classic curve. But what Lev found was that the low maturity shales had very little pressure sensitivity, and the high maturity shales had more. In other words, the high maturity shales almost behaved more like an elastic rock, where there's the low material shales were just like blocks of rubber. And I think this will be one of the last I'll show you. Here is the P wave anisotropy as a function of maturity. So on the left are immature, on the right are mature. And there's two pressures here. So red is low effective pressure and blue is high. So on the left, basically Lev showed that not all, but many of the low maturity samples were anisotropic and very little pressure dependence. So that to me would indicate that it's kind of a fabric. You know, there are perhaps lenses of kerogen in the background of clay, or lenses of clay in the background of kerogen. On the right, there can be high anisotropy. This is high maturity, but that maturity was more pressure dependent. So that makes it sound like, or at least Lev interpreted it as during the process of maturation, a little cracks were being formed along the bedding. Okay, let me just summarize. So, shale is defined by particle size, and shales can have a very large range of compositions. And they, therefore, can have a very large range of P and S velocities and seismic attributes that depend on composition, porosity, stress, compaction. Same with VPBS, it depends on composition, whether it's clay, silt, organics, carbonate. There can be different ranges of anisotropies. A shale will have low anisotropy if there has been a lot of bioturbation. Can be large if there's a very pronounced fabric. Adding silt and adding cement tend to reduce the anisotropy. And in kerogen-rich rocks, the properties, the velocities, the anisotropies seem to depend on the composition, but also the maturity. So, some of our many issues. Lab data are sparse compared with what we have for sandstone and carbonate. And we need lab data, to really push the science forward. Logs are also much more common, at least in the past, in conventional reservoirs than in shales. And so we're hoping to see logs and cores in this project. We don't have really many good models for shales other than the usual soft sediment, granular models and so on. But obviously there's a lot of improvement that's required. Organic shales have a tremendous range of properties. And so it's important for us to identify what's the question. During the last couple of years, I visited some of the majors. And I said, we're starting to work on shales, unconventional resources. What's the question? And most of the answers I got were, we're not sure. Do we want to look for porosity? Do we want to look for pressure? So that's part of the challenge here is certainly the Earth has many more variables than we'll ever measure. So it's important for us to understand site by site, what do we know the best, what do we need to know the worst, and so on. So, do we need to seismically or geophysically measure TOC? Do we need to seismically, electrically, geophysically measure maturity? Do we need to somehow remotely say something about the geomechanical properties like stress or brittleness and siltiness? That can be a part of the brittleness. It also could be part of permeability. So, feel free to add to our list here and help us identify those things that are painful for you. Perhaps we can help.